This is Professor Thompson, and this is exercise 1.432. And this specifically says to use the squeeze theorem. On your test, you'll have a squeeze theorem problem, but it won't say that. You'll just have something like this. And anytime you see a limit, especially on an exam, that looks like, I don't know the rules to know how to do this. This looks ridiculous. Chances are squeeze theorem is the answer. So they have the whole product. You take the square root of x cubed plus x squared, multiply that by sine of pi over x, and show that that's 0. And so, in your test, I guess I wouldn't already say that it's equal to 0. I would say find the limit. And so the way you find the limit here is use the squeeze theorem. You can't separate the limit into the product of the square root and the sine because the sine of pi over x has no limit. That's one we talked about in class already. So what you need to do is you need to show the squeeze theorem. So what you do is you start with sine because I want to bound that whole expression on both sides by something that has a limit. And so you start that idea by the fact that trig functions like sine and cosine are bounded themselves. Sine, no matter what the argument is, even though it's pi over x, it's always less than or equal to 1 and greater than or equal to minus 1 because sine always bounces between those two numbers unless you change the amplitude. And what you can do with inequalities, you can always multiply an inequality by a positive number. So you do, or by 0, it would just all become 0. So you have to justify that, and no matter what's in there in the square roots, the x cubed plus x squared, any output of a square root is always positive, right? You take in positive numbers, and when you square root them, you get positive numbers. So that means that the square root of x cubed plus x squared is always positive. So let's multiply this inequality by x cubed plus x squared. So multiplying that by negative 1 gives the negative of that expression. And then in the middle, you get the expression you're looking to work on. And on the right, if you multiply by 1, you just get the square root expression. So the middle is what you want the limit of, so you need to show that the two equations bounding it have limits that are 0, and so at least they have to be the same. So if they're both 0, which I think they are, then you say that the limit in the middle must be 0 because you're squeezed together. So if you look at those, you're using a lot of different rules together. So the fact that, for example, at the limit, so x goes to 0 of the square root of x cubed plus x squared, you're using a lot of rules together to get that, but one of the rules that we looked at was that rational and polynomial functions, the limit means you can just plug it in. So we do already know that the limit of x cubed plus x squared, as x approaches 0, that's 0 cubed plus 0 squared, which is 0. So that was one big rule that we had. Another rule is that you can take positive roots of any function. As long as the limit exists, the positive root will work the same. And the way that it works is that you can just take the limit of what's inside and then square roots. That was another rule in 1.4. And so that just gives us the square root of 0, which is 0. And the only difference on the left side is that you have a negative out front, but we also learned that constants, like negative 1, can come outside of limits. So by the same token, the other side will be 0. And so those two limits, if you have an inequality like this, yet another rule we had was that if you have inequalities, you can put the limits on each side, and the inequality will stay. So we start with this inequality. And that's still true if we put the limit as x approaches 0 on all of these. What I just showed on the previous slide is that I know the limits on the left and the right. And so I can evaluate those and say, well, those are 0. And because I'll have the same numerical bound now on the left and the right of the limit in the middle, it's going to exist and be 0. So that right there, the inequality of 0 on both sides tells me that the limit as x approaches 0 of the square root of x cubed plus x squared times sine of pi over x. That whole thing is 0. And so that is the entire problem. And so it also helps when you're doing this to mention that what you're using is the squeeze theorem. There you go.